Let's see. All right, so we've got a couple sections in one more chapter, and then we'll be ready for test 2. So test 2, what did we say that was going to be? The 20th, is that what we said? You may have it right now. I think the 20th is what we said. I'm sticking to whatever we said before, but I think it's the 20th, so that'll be a week from Wednesday. So the plan is, okay, we'll do 7-1 today, 7-2 Wednesday. Okay. And that'll make Friday Hawks Day. Get caught up on it if you want to come, and then Monday, a week from today, it will be test review. And then Wednesday, test 2. Okay. I think that's where we're at. So on test 2, we've got 4-1, 4-2, 4-3, 4-4. And then 6-2 and 6-3 that we just finished with the geometry stuff. And then these 2 probability sections that we'll do this week. All right. Thursday I have to turn in midterm grades, so really Wednesday night, Wednesday evening, because I do it like 8 a.m. on Thursday. So the midterm grade in here will be your test 1 averaged together with whatever your Hawks grade is at that time. Okay. So for most people, midterm grades don't matter for anything. Okay, but if you're concerned about your midterm grade, the thing you can do between now and then is make sure you're caught up on Hawks. Okay. I have any questions? Anything you can think of? Okay. All right, so we'll start looking at chapter 7. Chapter 7, we're just doing a little bit of probability, and we're not getting crazy with it, like with most of the sections or most of the chapters in this class. We just kind of get the basics and then go on to something else. So that's what we're doing, especially in 7.1. We're really just looking at the basics, and then we'll get just a little bit deeper in 7.2. 2. If I said 3, I might have misspoken. It's test 2 that's due. That we'll do the 20th. Test 3 will be right before Thanksgiving break. That week before Thanksgiving break. No, not this time. Yeah, we've done it in the past once or twice, but they didn't schedule us one this year. And something else that's different, if you're used to being around, okay, we don't have any like dead days. Okay. Classes end December 1st, and then finals start the next day. Okay, so probably most of your classes will not be doing anything those 2 days after Thanksgiving, though, other than getting ready for a final. So, okay. All right. So, well, look here. We're just going to calculate some basic probabilities in this section. Okay. All right. So we've got a little bit of vocabulary we need to get to, and we'll look at the definitions here in a second. But if you hear the term trial or probability experiment, okay, our meaning then is we've got some procedure we're going through, and we don't know what the result's going to be until we do some type of probability experiment. So that's some type of experiment where we can figure out the probabilities of what will happen, but we don't know actually what the outcome is going to be until we do the experiment. Okay. And the example that we're given here is drawing a number from a hat when we got 1 through 10 in the hat. And you don't know which number you're going to draw until you actually draw one. And we can figure out like how likely it is to get one number or another, but that would be a probability experiment or a trial. Okay. And then we talk about the individual results, and those are what we call outcomes. Okay. So there we would have 10 outcomes. We could draw the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. We would have 10 possible outcomes. Okay. So the first thing we kind of want to focus on here is listing out or being able to, in this section we're listing. And we want to be able to list out all the possible outcomes of a probability experiment. So that's what we call the sample space. Okay, so if we go back to our example of drawing a number 1 through 10 out of a hat, okay, if we've got all those numbers in the hat, then our possible outcomes is either we draw a 1, we draw a 2, or a 3, or a 4, all the way up to 10. Okay. And the way we write these down should look familiar. We put them between two curly brackets and separate each one with a comma. That's like a set. And we write it like a set. Okay. We'll call our probability space. Our sample space, sorry. Okay. So let's see if we can come up with a couple sample spaces here. Let's look at these. Okay, we want to identify the sample space for each one of the following experiments. Okay, so A says we're rolling a single die, so if it doesn't say, it's talking about 6-sided die. Okay. So we want our brackets. Okay. And then what are the possibilities if we're rolling a 6-sided die? What could we get? What numbers are on a 6-sided die? We got 1, 2, 3, 4, 5, and 6. That's it. That's numbered 1 through 6, so there are possibilities for rolling a 6-sided die, so that would be what we call our sample space. Okay. B's a little bit trickier because we've got two things happening. Okay, B says birth order gender for 2 children. Okay. So we just want some way of labeling these. I don't know, I'm calling boy, girl, I guess. Okay. So the thing to think about here is, since we're talking about birth order, the order matters. So like maybe we could say boy, boy, or we could have boy, girl, or we could have girl, boy, or girl, girl. Those would be our possibilities there. That would be our sample space. Okay. So you could write them all the way out if you wanted to, but usually we're trying to be brief and not write so much down, so that would work on that one. Okay. Questions on the sample space? The sample spaces can get really complicated. Okay. If you have a whole bunch of things happening at once, and then they can get really complicated. We're not going to get too complicated with it. Okay. And we will have some where we have 2 events, like here we had the 2 children. Okay, but in general, we're not going to get too complex. Okay. All right, let's look at another one. This one, again, we've got 2 events, so a little trickier. This one says identify the sample space for tossing 2 coins together. Okay. So if we toss a coin or flip a coin, we've got 2 outcomes for that one coin. What would our 2 outcomes be? We either get Heads or tails, yeah, so maybe we can just use H or T for heads or tails. But here we're flipping 2 coins. So maybe we could get heads on both. It's heads. Or heads on the first, tails on the second. Or we could get tails on the first, heads on the second. Or we could get tails on both of them. So that should be all of our possibilities there. That would be our sample space. Okay. Hey, these on Hawks, they like to make long. So I didn't give you many. And I tried to give you the shortest ones I could. So you're not having to make a huge list on things. Sorry that they're as long as they are. This would be nice if we had some problems like this, we could do that. They usually give you way too many choices on the Hawks problems, unfortunately. Okay, so just quick review of vocabulary here. We'll get the actual formal definitions. So we're doing a trial or a probability experiment. That's some process that we're doing, some procedure we're doing where we have a random result. And when I say random, I don't mean we can't figure out probabilities. I just mean we don't know the actual result until we do the process, okay? Like flipping a coin. Okay. And then the outcomes, that's the name we give to the individual results we can get. So that when we do our probability experiment of flipping a coin, then we have 2 outcomes, heads or tails. And then if we list all the possible outcomes, we get a sample space. We've got one more term here that we haven't talked about yet. That's what we call an event. Okay. So an event here is when we're thinking about a group of possible outcomes. Okay, so outcomes are each individual thing that can happen. Okay. And events if we're grouping some of those together. Okay, so we're taking like a subset. So maybe with our coin flip, let me go back just a second. Here we've got our sample space. So maybe an event we could say is we could talk about the outcomes where we have at least one head. So that would be these 3 outcomes. Then our event would have those 3 outcomes in it. Okay. So an event, we're just coming up with some way we're taking a group of outcomes. Okay. And that's typically what we do when we're thinking about probability. Okay. And we take a group of outcomes. Okay. Questions so far? Got that mostly just been vocabulary? All right. So we're going to look at 2 ways we can think about probability. Okay. We got our terminology behind this as far as sample space and all that. Okay. We'll have 2 different ways we're going to think about probability, and both of these are used in practice. Okay. The first type of probability we're going to look at is what we call classical probability. Okay. So with classical probability, we're thinking all of our outcomes are equally likely. Okay. And then we can calculate our classical probability this way. Okay, it says we take the number of possible outcomes in the event. Okay. So whatever we're looking for, and the outcomes that have the characteristic we're looking for, divided by the total number of outcomes in the sample space. So we just take the number of outcomes that have the characteristic we're looking for and divide by the total number of possible outcomes. Okay, and the idea with classical probability, the thing that sets it apart, okay, is that with classical probability, you can think about it like theoretical. Okay? We have an idea of what the probability of each one of the outcomes is going to be. Okay? So then we can calculate that and divide it by the total number of outcomes possible in the sample space. Okay? It'll be a little easier to see the difference once we see the other type of probability. Okay? Down at the bottom, one thing to mention, probability is always between 0 and 1. It says inclusive, so it can be 0, can be 1. But with probability, we normally don't talk about a probability less than 0 or bigger than 1. Okay? Because if we have, you can think about it as percentage. Right? So if we have a probability of 0, that means there's like a 0% chance of something happening. If we have a probability of 1, that means there's a probability of, or there's a 100% chance it's going to happen. Okay? So normally we don't think about being able to have less than a 0% chance of something and more than a 100% chance of something. Okay? So typically we treat probability as a number between 0 and 1. Huh. So let's look at a classical probability. And says, suppose we're asked to draw a card from a standard deck of 52 cards. We got the picture with all the cards. If you're not familiar with the cards in each deck, so we'll refer back to this. I've stretched it out and made it as big as I could. Okay. We'll come back and use our picture. Okay, this is in Hawks too. If you hover over where it says deck of cards, it'll pop up the picture. So you don't have to have it memorized. So let's look at the first one here. A says, what's the probability that the card you draw is red? So we've got, or to do classical probability, we need to figure out how many red cards we have. Okay. Because we are counting the ones that have the characteristic we're looking for. So here, there's 13 of each suit. So if you remember that, you don't necessarily have to count. So there's 13 diamonds, 13 hearts. So if we'll put all those together, we've got 26. 26 out of 52 cards in the deck. Okay. So on A, our classical probability, we would say that's 26 out of 52. And if we write that as the simplest fraction, that's 1 out of 2, or 0.5. You could say it as a decimal too. Questions on that one? We're looking for red cards. 26 of those out of 52 total. 0.5. Okay. All right, let's look at B. B says, what is the probability that the card you draw is a diamond? Okay. So if you count, you can count if you need to. Okay. We've got 13 diamonds out of a total of 52 possible cards. So same idea as the last one. And we've got 13 that are in our event of being a diamond out of 52 total possible outcomes. As a fraction, that's 1 out of 4. Or as a decimal, that's 0.25. So either one of those is okay. Questions on that one? C says, what's the probability the card you draw is a face card? So that's a king, queen, or a jack. Okay. So look back at our cards. We've got a king, queen, and jack of each suit. Okay, so 3 in each suit. So 12 face cards. Okay. So 12 cards in our event. Face card out of 52 total cards. So let's see, 3 out of 13. I have no idea what that is as a decimal. Let me check. About 0.231 as a decimal if you want to use a decimal. And D puts 2 conditions on our card. Okay, so we've got 2 conditions on our event here. D says, what's the probability of drawing a red? So that's one condition. And then spade, that's another condition. And also it's a weird one, because if we look back at our card, these are our spades. How many of these are red? 0, right? Spades are black cards. Right? These are our red cards, hearts and diamonds. Clubs and spades are black. So we don't have any red spades. So what's our probability going to be? 0, yeah. So we would say 0 out of 52, and that's just 0. Okay, so look out for weird stuff like that. Questions on those? That's just classical probability. Yeah, let's look at another one. I'll get through these here. Oops, sorry, too far. Okay. This one we don't have to do it with cards. Okay. It says, suppose you grab a snack from a bag of chocolates that contain 4 caramel, however you want to say that, with milk chocolate, 4 peppermint with white chocolate, 6 dark chocolate with mint, 2 raspberry with dark chocolate. What's the probability that you randomly grab a raspberry with dark chocolate for your snack? I'm sorry, say again? Yeah, all right, so let's see. So we've got 2 raspberry with dark chocolates in there, right? So that's how many we have in our event. Out of, then we need to figure out the total. All right, so total, you may be right, I just haven't added it up yet. So I've got 4 of the first kind, 4 of the second kind, 6 of the next one, 2 of the last one. So yeah, 16. So 2 out of 16. So we could call that 1 out of 8, or that's 0.125, yeah. So we simplify it, then so we get 2 out of 16 is correct. It's just not in simplest term. We just take how many outcomes are in our event, divide it by how many total outcomes we have. So not bad. Okay. That's classical probability. Okay. The second kind of probability we're going to talk about, okay, is called empirical probability. Okay. So with empirical probability, we don't necessarily have a number for the total possible outcomes. Okay. So this comes up with like, maybe we're giving a survey to people, right? We're taking a poll. Right? If I wanted to know the probability that a person's favorite pizza topping is pepperoni, well, you could do that. You could ask a bunch of people, see how many of them say pepperoni out of how many you asked. But if you ask more people, it changes the number we divide by. So we don't necessarily have like a cap, a maximum on what our bottom number can be. Depends on how many times we do our experiment. So empirical probability you can think of as experimental probability. That's another name for it. So classical probability, sometimes we'll call that theoretical probability. Empirical probability, you can think about it as experimental probability. So formulas, same idea, it's just we've got a different situation. Okay, so here we count the number of times our event occurs out of how many times we did our experiment. Okay. And it's still going to be between 0 and 1. Okay. So let's look at one. All right, this one says for her elementary school science fair project, Libby is conducting research on the accuracy of the weather prediction from her local news channel. She recorded the forecast and the actual weather for 2 weeks. And then we've got a table that has her results in there. So here's our table. So the left column has the forecast. The right column has the actual weather for that day. We'll come back to this. Okay. It says using empirical probability, what's the probability that the news channel accurately predicts the next day's weather? Okay, so we're using empirical probability here. So what we want to do is we want to count how many times they got it right out of how many days we checked. Okay. So let's go through our table and see how many of them match up. Okay. So looks like the first day, we'll count this one. We've got rain, rain. Second day we had a chance of snow and it rained. I guess we're not counting that one. Okay. Third day we had snow, snow, so it matched then. The next one's cloudy and clear, so that one didn't match. Then we got cloudy, cloudy, so that one was right. Then rain, rain, so that one matches. Then we got clear and some drizzling rain, so that didn't match. Clear, clear matched. Cloudy, clear doesn't match. Chance of snow and cloudy, I don't really know how to count that one. I guess since just she didn't say chance of snow was her actual weather, I guess we'll leave it out. Clear, clear will count. Got another clear, clear will count. Rain, rain will count. Chance of rain and cloudy. Guess we won't count that one. We'll just do the ones that match exactly, I guess. So how many do we have that match? So we had 1, 2, 3, 4, 5, 6, 7, 8. Okay, that were spot on. So we had 8 that match out of 14, yeah, 2 weeks, so that helps, right? So 14 total. So to get our empirical probability, do the days where the forecast was right out of the total days we checked. Okay, so let's see what that is as a decimal. So 8 divided by 14. That's 0.571 something. So we could give our answer as a decimal, but usually something like this, right? It'd make more sense to think about it as a percentage. So if we move our decimal place 2 places to change it to a percentage, that would be about 57.1%. How accurate they were. So using empirical probability, we would say the probability that we get the next day's weather is about 57%. Okay. Now, the only way we could do this as classical probability, okay, would be if we checked every day. Right? We would have to have a list for every day that they've predicted the weather and the actual weather for every day. But that's going to be a lot of work. Okay? So instead, we're using this empirical probability idea. Okay? So with the cards, if we're drawing cards, we can figure out all the possibilities, right? We can figure out all 52 possibilities of what card we could draw. So we can do classical probability. Here, that's not practical. Not practical. Okay. Questions on that one? Okay. Now, these last three, let's just figure out, would this be empirical probability or classical probability? Okay. Let's think about that on these. Okay. We want to know, would this be classical or empirical probability? So A says Katie's curious about her chances of winning an e-reader from the Student Government Association. She polled her friends to find out how many of them filled out the survey to be entered in the contest. So this one's not going to be classical because, okay, let's think about it this way. In order for it to be classical probability, she would have to know how many people total filled out their survey, right? She would have to know how many that in all there were, right? But on this one, she didn't do that. Instead, she just talked to her friends. So it's like she just talked to some of the people and figured out if they entered the survey. So she's just doing her own little experiment here. Okay. So this one would be empirical. Be empirical. That is a little tricky. Okay. B says Tristan's interested in his chances of winning at the blackjack table. He determines the probability of what his next card will be by knowing the cards that have already been played. What do you think about on that one? Does he know all the possibilities? He knows all the possible cards that can come out, right? And he already knows the ones that have been played, so. On that one, I would call that classical probability. Okay? Because he knows what cards are left in the deck, right? So he knows all the possibilities that he could get. So that one would be classical. That one's tricky. I think that would be classical. Okay. Look at one more here. Okay. It says, based on the recent United States Census, the local government estimates the amount of growth the community will experience in the coming years. Okay. This one is a gray area for sure. Okay. The idea behind the United States Census is that they collect data from every person. So if that was actually the case, if they actually got data from everybody, then you may be able to call this one classical. Okay. But in practice, okay, in reality, you don't actually get everybody. You try to get everybody, but you don't. You always miss some people. So this one would really be empirical. So this one's kind of gray area there. So that's the main idea. If you know all the outcomes, okay, and you can divide by the total that there are out there that you could possibly have, then that's classical probability. Okay. If you're just collecting part of the information, okay, and that would be empirical probability. Okay. And I'm not going to give you any like super tricky anything. So. Okay. Questions on those? Okay, pretty short section. We're done in that section. Just the basics probability. Next time in 7.2, we'll talk about if we have situations where it's a little harder to find how many possible outcomes we'll have, some techniques we can use to figure out those numbers. Okay? We'll be doing next time. If you didn't get on the sign-in sheet, make sure you get on there before you leave.